So, thank you for the introduction. So this is the last talk for today. I hope there's still enough oxygen in this room that you can follow me. I studied groundwater science in Dresden, and at nearly every lecture, maybe except mathematics, informatics, and law, the professor showed us any version of the water cycle. And what I'm going to talk about today only concerns the groundwater, which is the water below the surface that we usually do not see, but many of us are consuming every day. And these groundwater resources, they are threatened, they are often contaminated. And so a big part in the work of my colleagues and me is that we are dealing with this groundwater contamination. We have scientific models we are working with in order to understand what is happening down there with the water. So whom of you is a chemist, in chemistry? Is there any chemists here? Some, okay. Is there some geochemistry knowledge here in this room? No, probably only Mike. Yeah. So this is why I want to do a little introduction in the field that I'm dealing with. And the problem today is I want to show you a graphical user interface which I implemented in Python, and it's using PyQt or PyQt, which is roughly the same. And I want to enable the engineers that are not able to use our scientific software to work with it by applying this graphical user interface. So this user interface deals with iron in groundwater, is modeling the things that happens there, and why actually iron is a problem in groundwater. Anybody can imagine why iron is a problem in water that we drink? Maybe you have an idea. you actually can't see it, but sorry. Going this direction. Iron appears in two forms called two redox states. Normally the iron in groundwater is reduced and you cannot see it in the water. But in contact with oxygen it's getting unstable. It's oxidized to ferric iron, and then you have this precipitates, and you probably do not want to have them in your sink or in your armatures or in your pipes, so this is just making problems. So many groundwaters naturally contain this iron dissolved, and when we want to use this groundwater as drinking water, this would happen. So we need to get rid of this iron in the water, and there are many different methods how to do this. Many of them are happening above ground, above the surface, but there's a relatively new approach that uses that happens in the underground. So we say in situ, where the groundwater originates from. The advantage of this in situ removal of iron from groundwater is that the aquifer, the part of the subsurface, works as a reactor. So this method is quite cost-effective alternative to the common above ground treatment. The operation principle looks like this. You have a well where you pump off your water, and a part of this water is supplemented with oxygen and re-injected after the pumping into the aquifer. So the oxidation of iron happens here inside this aquifer. And the operation principle is then that you as you do alternating pumping and injecting, so you re-inject a part of this oxygenated water. So usually you do not only have one well, but a whole group of wells. So this is a method which is increasingly used to treat groundwater, to use it for drinking water. And the dimensioning of these wells from the engineers is so far often done just empirically. So they have their knowledge about the concentrations and they roughly estimate at which rate they have to pump, how much oxygen is necessary. But this doesn't work so well for every cases. I just want to show you what's actually happening there in the aquifer. There's a whole bunch of reactions going on there. The most important, maybe for you just to know now, is that the iron, which is at starting time there in the groundwater, will be oxidized from the oxygen when you infiltrate this oxygen-rich groundwater. And in the second step, this iron is precipitated. And so it's stored there in the aquifer, which is your reactor. And after infiltration, there's a recovery phase of the well. Then there's no more dissolved iron anymore, and your water has a much lower iron concentration, so you can use it for tap water. So what I did, the task, as I said, for the engineers, that they need to know the pumping rate, the duration of the pumping phase, and the oxygen demand. And I created a graphical user interface in Python, which uses a predefined two-dimensional hydraulic reactive transport model for one single well. And this one calls the simulation software. Anybody here having heard or worked with ModFlow? Probably only Mike. FreakC, somebody? Is there someone working with FreakC? This is a chemical simulation tool. Yeah, probably it will take you a lot of time to get started with it, but hopefully if you would want to use Finario, which is my software, it would be much easier for you to get started, because I designed it to make it just easy to use. And the third scientific simulation software that is called from Finario is PhD 3D, and this actually does the final reactive transport. So the outcome of Finario, this is, you can print this plots, and you can also, we have the data as text files you can access, and you can do your own post-processing if you want to. So this is the main overview of Finario. The name is coming from Fe, iron, the chemical acronym. Then you have scenario, and you have the O from oxygen. And I implemented a version just recently in Python 2.7.9 with Qt, and I applied PySide, which is roughly the same like PyQt. And I am working on Windows because everybody in our field of engineering science works on Windows. So this has to work. As I said, the target user is not a very specialized power user, so the design and the layout of a Finario should have been clear and self-explanatory to avoid errors in the input for the user. And so I adapted the layout. So maybe I just switch over to Finario itself here in the foreground now. So I have three views actually here. In this first one I can define hydraulic parameters. In the second view I can define the chemistry of the ground and the infiltration water. And in the third one, finally, I can define some transport parameters. As you can see, actually everywhere I tried to explain the parameters that the user can define. So there is here a scheme of the model and a description of the parameters. So just proceed with the presentation. This is what I said. We have these three views. And of course you also have in the application you have your menu bar, and you have a status bar below the main menu. For example, you can see tooltips when you hover over special elements, so the user can just read what's going to happen if he's clicking here or there. So with PyQt or PySite, you can just make application surfaces, graphical user interfaces, as we are used from high-end applications. So there's a special concept when you define your data. For example, when I want to change these height of the model, I can click here, and if I try to input just not a number or figure, just typing a letter, this won't be possible. And this is because with PyQt you can just take care about what the user actually should be able to do. This is the so-called model view architecture. You have a separation of the data representation and the view to the data. So PyQt comes with predefined classes for the view of the data at this user interface, and we have a model that reads and writes the data from the container, or the data themselves are stored in a file, for example. And in order to handle this very specified behavior of these spin boxes here, if you want to edit this, you can define how many digits there will be, for example. No digits, this is an integer. There's another spin box open, this is a checkbox. And all this behavior you can define in the so-called delegates, which mediates between the model and the view. So you can actually avoid that the user just makes a wrong input. So it looks like this. Just skip over this. Another thing is that you have signals and slots. I think most of you know that signals, they are emitted whenever the state of a widget in your graphical user interface changes, but by default they are ignored, and the slots, they are catching these signals, and you just actually define some methods there. For example, if I use this push button execute flow simulation, this slot here, mod flow, I called it, is processed. And I use the subprocess call to run the mod flow in the background. There's a lot of other things happening here, which I just commented out. Finally, after mod flow is finished, you will get this message. And you can also save your different scenario runs, give it a name, and there are binary files, which are here the red ones, that are created from Finario software. So I decided not to incorporate this scientific simulation software into Finario, but the user can install it separately. And another aspect is that I do not write all the input files for this software from the scratch, but I use predefined input files, and I just make the changes regarding to the parameters the user adapts. And this is how the model actually looks like. Here's the well in the middle. The whole area is used for the hydraulic modeling, and only a part of it for the reactive transport, because this is what takes a lot of simulation time. This is the implementation structure, which is quite large, and just to get an impression, I don't want to say anything more about it. Here's the main window. We have Python libraries, Python modules for the layout and for the dialogues, and other ones for the data models and tables. And the simulation software is externally, of course. So just an example from a use case where you have a well with 19 hours injection of oxygen-rich water. The groundwater has 0.38 millimoles per liter iron 2. Then after injection, there's 3 hours of reaction contact time, and afterwards you have, of course, a longer time of recovery of water. And this is not a pattern for wallpaper, but this is the result of this model. If you look at different distances from the well, you see far away from the well the concentration does not change over time, but close to the well during injection, you can see here injection is the first one, then you have the contact time, and during the recovery, of course, iron concentration increases again, but this increase is actually getting less and less after 10 cycles of this pumping. But it's asymptotically decreasing towards a certain concentration. Another thing, you can see that the oxygen is consumed. You can see a tracer which is introduced with the same concentration, but it's traveling much farther because it's not consumed. And I've made a comparison with measurements from a specific site, and the iron concentration and oxygen concentration after recovery and after infiltration behaves roughly the same at this special site as the model could do in this example case. Of course, I would like to do something more with Finario. There are some more processes I would like to implement, and also I would like to improve the graphical user interface behavior. There are some ideas. If anybody of you wants to start with graphical user interface programming, I would strongly recommend Mark Summerfield's book, Rapid GUI Programming with Python and Qt. And you can just switch over to PySite very easily because there are just a few differences between these two libraries. And you can also watch Eric Thompson's PySite port of Summerfield's book on GitHub. Yeah, that's all I wanted to say. Thank you for your attention.
Any questions?
So thanks for your talk. You said you were talking to, so you're using 3 scientific tools in the background that you're using for generating these graphs and stuff. So how do you exchange data with those? Are they Python tools, or do they have a command line interface, or how do you get data in and out for them?
You mean the data exchange between the scientific software and
your
the Finario?
front end? Yeah.
It's just this Modflow, FreakC, and PhD 3D. They just read their input from text files. So I just need to change these text files and then calling the software.
Any other questions? Oh, sorry.
It's just a hint on the questions. I think you use subprocess call. You might use maybe check output or something. So if this thing dies, then you can't get the error message. Maybe, or you use a pipe to get the output, the standard output, standard error. That would be something. Otherwise, if it dies, you don't see anything. So if the Modflow doesn't converge or something, you won't see anything. And the other question is, if you oxidize, so iron in subsurface, does it clog the aquifer in the long term?
Well, this is the first we can discuss afterwards, because I tried to catch some errors already with another method. Mike has a good idea, because if you precipitate this iron, then the pore space, of course, decreases. So you may block the aquifer actually, so it's not working anymore. So what the engineers are doing, they are trying to have this reactive zone not directly to the well, but a bit far away. Maybe I have a picture actually that these iron precipitates where is it? No, I deleted it. That they first inject water which is free of oxygen during the first cycles, and then the oxygen comes later, so the zone is actually some meters away from the well, so the reactor volume itself is also increasing because it's farther away from the well.
Okay, well, thank you.